Welcome back to The Explainer. Today, we're dropping straight into the danger zone. Picture a dark, mystical study space. You're the student, the tension is high, and hovering right in front of you is a massive, glowing blue and gold holographic UI. We're stepping into the GATE trials to master binary overflow and fractional illusions. Let's power up our focus and face our first challenge.
Here is boss number 1 from the GATE 2019 exams looming right over us. So, if z equals x minus y, and both x and y are n-bit sign magnitude, what size must z be to completely avoid overflow? Okay, deep breath. The stakes are high, but to beat this, we just need to understand the core magic system of this world.
So, what actually is binary overflow? Well, in this digital realm, overflow hits when you take two numbers that have the exact same sign, say two positive numbers. You add or subtract them, and boom, the result forcefully manifests with a completely different sign. It's like channeling two massive bursts of positive energy, but the output is this dangerous negative blast. It basically means the container you're using for your calculation just isn't big enough to hold the power.
Let's look at exactly how this breakdown happens in a standard 3-bit signed binary system. Remember, that far left bit dictates the sign, right? 0 is positive, 1 is negative. So positive 3 is 0, 1, 1, and positive 2 is 0, 1, 0. You add them up and the raw binary math gives you 101. But wait a second, look at that far left bit. It's a 1. In this system, 101 represents negative 1. The math literally rejects our calculation. Imagine a glowing red barrier of error just violently blocking it. We expected a positive 5, and instead we got a negative 1.
And that right there is the overflow barrier. The 3-bit space simply cannot contain the sheer magnitude of our result. The number 5 basically spilled over, crashing into the sign bit and corrupting the whole answer. When the signs align like this and push the magnitude beyond the limit, that red error barrier is triggered. Our current constraints are failing. We are going to need a much bigger container to survive this.
But here is our breakthrough. The absolute easiest way to shatter that barrier entirely? You just extend the bits. If x and y are trapped within n bits, our result z needs exactly one extra bit of breathing room, n plus 1. By upgrading to n plus 1, we give the magnitude enough space to grow, ensuring it never, ever corrupts the sign bit again. The red barrier shatters, and our first green orb of victory is secured.
Boss 2, Fractional Illusions.
The holographic UI shifts, and now we are staring down a completely new, complex, glowing puzzle. We've got a specific structural constraint this time, a binary format consisting of bits B7 down to B3, then a fractional dot, followed by bits B2, B1, and B0. So that's 5 bits for the integer side, 3 for the fraction. The enemy's trap is this: which decimal values cannot be exactly represented by this specific bit structure. We're going to be shown what look like totally normal decimals, and we have to deduce which are true and which are fake illusions.
Now, to break an illusion, you first need to know the absolute limits of your reality, right? Let's build up our power level and calculate the max boundaries of this system. Over on the 5 integer bits, if we max them out and turn them all to 1s, we get 16 plus 8 plus 4 plus 2 plus 1. That equals 31. For the fractional side, the bits represent halves, quarters, and eighths. Maxing all 3 of those out gives us 0.5 plus 0.25 plus 0.125, which totals 0.875. Put them together, and the absolute maximum value this reality can hold is 31.875.
But here is our secret weapon. What is the absolute minimum step we can take? If we only ignite the very smallest bit, B0, the value is exactly 0.125. That is our atomic unit here. You can have 0, or 0.125, or 0.250, but absolutely nothing in between. So if our minimum stepping stone is strictly 0.125, then any value ending in something like 0.100 or 0.001, those are fatal flaws in the enemy's trap. They are mathematically impossible illusions. You literally cannot stack blocks of 0.125 to perfectly build a 0.100.
Okay, so with that realization, the final attack sequence begins. Lock your eyes onto these 4 targets. Option 1 is 31.50. Option 2 is 0.875, option 3 is 12.100, and option 4 is 3.001. Armed with our max limits and our secret 0.125 minimum step, let's see which ones actually hold up to reality.
Let's apply our logic and end this.
Option 1, $31.50. Well, 31 is safely inside our integer max, and a 0.50 fraction is just turning on that single B2 bit. That perfectly works. It glows green for truth. Option 2, 0.875. We already proved that earlier. It's just turning on all 3 fractional bits. Green again. But look closely at options 3 and 4. 12.100? No way! You absolutely cannot reach 0.100 when your smallest possible building block is 0.125. And 3.001? Not even close. You can basically see these impossible decimals crashing into red barriers and exploding. They are structural impossibilities.
And there is the final victorious blow from the GATE 2018 exam. Options 3 and 4 cannot be exactly represented. By simply understanding the true weight of binary fractions, the 0.5, the 0.25, and that crucial 0.125, we easily saw straight through the mirage. Green light washes over the scene. Challenge cleared. We've conquered some genuinely complex concepts today. We used the crucial n+1 rule to completely sidestep sign magnitude overflow, and we used the strict 0.125 step limitations to shatter 3-bit fractional illusions. The rules of this system, they don't control you anymore. You understand them. So, picture those cinematic rays of light breaking through the dark study room. Maybe a few sakura petals falling for dramatic effect. You're victorious. Now that you know how to see through the matrix of binary limits, will you conquer your next trial? Keep that focus sharp, and I'll catch you in the next explainer.